तेजस्विनावधीतमस्तु मा विद्विषावहै।
We were looking at the design for adder subtractor design, in which we had added 8 numbers n0 through n7, and we got a sum here which is 3 bits more than each of these bits here, and this last bit is the sign bit, so also the case with sum here. And we had seen that the whole thing was pipelined and a partition for data width as well as the functionality. And here in this example the functionality happens to be same add or subtract, and when we take up bigger applications such as DCTQ, we will appreciate the functionality difference coming in. And we had 3 stages of pipelining here, and with 5 internal registers used as pipeline registers. And note that the last sum is not registered, and we had seen how to take a 2's complement of a number, signed number, and these were the examples we had considered earlier. And now let us have a look at the Verilog code for this adder subtractor. So I will add 8 12-bit 2's complement numbers n0 to n7. There are 5 pipeline stages registered at positive edge clock. The result sum is in 12-bit 2's complement not registered. There is a mistake here. Sum must be 15 bits. And we will have to first declare the module, and this is the module name we are giving, and you can, if you want, you can designate as 8 into 12s, because there are 8 inputs, and clock is one of the inputs, and n0 through n7 are the 8 numbers, and so what we have here is it is each of them is the 12 bits, and that is why we declare this here, and the clock is also declared. So also the case with output, in which case the sum is of width 15 bits, and that is the output listed there. So during the course of the other statements that we will actually work out the arithmetic portion, we will be encountering very many signals, intermediate signals. Some of them may be with assigned statements, and therefore they are all declared as wire, and width of each is also declared here. And for example, we will be adding LSB as we had mentioned in the pipeline partition earlier, and we will also be adding MSB with the carry of the LSB addition and so on, and they all have to be declared here. And there are also numbers N0 through N7 which will have to be propagated, which is not computed at a particular stage. For instance, MSB has not been computed, therefore they have got to be registered and propagated through the pipeline in order to process when the time is ripe for that. And there are other similar next stage MSBs, LSBs listed here, and they are all declared as reg here, and so is the case here. This is the second stage, 1 stands for the second stage and 0 for the first stage. So once again you can see 1 0 second stage of MSB registers. And so this completes the reg wire declaration, and we also need some carries, that is what we are doing. The final result will be here, and actually the ultimate result will be in assign statement, therefore that is not listed here, but it had appeared elsewhere. And the first statement is, so as we mentioned before, in the first stage what we do is we add two numbers at a time, N0, N1, and we add only the LSBs of this. So for example 7 bits only are added, and in parallel, that is concurrently, we add other numbers as well, N2 and N3, and using this assign statements, and the result is put in this assign statement is declared as wire. So this is nothing other than a combinational output. And so similarly we have S01, S02, S03 rising from adding other numbers, so N2, N3 here, N4, N5 and N6, N7. That is to say, we add using 4 adders concurrently, so that this is at the first stage, and in the we add just the LSB, and we latch or rather register when the first clock arrives at the positive edge, and this is the pipeline 1 and clock 1, register MSB to continue addition of MSB. See, since we are not adding the MSB, we had to register it separately, that is what we are doing here. This is the MSB for all the numbers, and then propagate it for use in the next when the next clock arrives. So before the next clock arrives, we will be doing this, we are also preserving the sum, this is LSB sum, and that is also being preserved here in all this. So we had 4 results by adding 8 numbers, that is why S00 through S03 will be the LSB result. And before we add the MSB, we should not forget to extend the sign, and this extension of the sign is merely duplication of MSB. This is the MSB 11 through 7, and this is the sign bit. So what we need to do is we have to just duplicate here, and the whole thing is concatenation. That means to say it is first we write the duplicated sign bit here of this number called N0 reg 1, that is registered at clock 1, and the whole thing put together is a sign extension of the MSB. To this we had to add second number, and that also follow the same standard style here. For example, this is the sign extended bit, and this is the actual MSB bit of N1, and to this we have to we should not forget to add the carry resulting from the LSB addition, and that is available in this. This was the last bit in the final result of LSB addition, and that should not be forgotten here. So to make total addition here, that is in and same is the case for other pairs of numbers, for example N2, N3, then N4, N5, then N6, N7. So in this case S00, S01 through S03, all of them are assigned statements, and this is pre-computed, because this being a time consuming thing, we want to speed up the system, therefore we pre-compute, and then only with the following clock edge we assign these values to the another set of registers. And here we have this, we preserve this all MSB sum which we had computed earlier, and in another register the same nomenclature we use, except that this is clock 2, so we add just reg 2 to discriminate from this one, and this will have to be used in the subsequent stages. So, here what we do is we should also preserve the LSB sum, and because we have not yet fully made total result of the first stage, and this completes the very first stage of addition that we have seen in the partitioned pipelining approach, and the diagram we have seen earlier. And in the second stage what we do is we have from the first stage four results coming, S0 not through S0 3, and that we are going to add here. So, once again we adopt this very same strategy that we had done earlier. We take the whole number and bifurcate into roughly equal numbers, and call it LSB and MSB, and then add only the LSB first. So, that is what we are doing here. This LSB is added at the first stage is S0 naught, and to the S0 1, that was also the first stage output, second output. So was the case, so is the case for S0 2 and S0 3, which is the other two outputs of the first stage, and we designate it as S10 and S11 as far as the LSB sum is concerned. This is the LSB sum, and this will naturally be the carry resulting here, which will be adding with the MSB later on. And now what we had to do is, when the positive edge of the clock is encountered, that is at clock 3, and we will register MSB to continue addition of MSB later on, and we have also to preserve this LSB sum because we need it at the end, and that is what we are having here, S10 S11 here. And so in this case what we need to do, this is the second stage, so there will be only two outputs here, and this is MSB. So we need to preserve the MSB here, that is LSB and this is MSB, and to continue the addition. And as far as the MSB is concerned, we are going to add in this fashion. For example, this is the second stage, so we have added only the LSB earlier, and we have to continue adding the MSB along with the carry that was generated in the LSB addition of the first stage output, and that is this one here. And as usual we concatenate the sign extended bit as well as the actual number of MSBs, that is here, and so is the case for the first output of the first stage, and this is the second output. So when we add this together, out comes this result, which is also an assigned statement being a combinational output, and note that we have added the carry here. So that is what the comment says here, add MSB of second stage with sign extension and carry in, this is carry in actually from LSB, actually LSB carry out becomes the carry in for this MSB, and it also results in one more bit which is nothing but a duplication of the same sign bit, therefore we ignore that. And next what we do is, we will what we do here is we have MSB here sign extended, and this is also MSB once again sign extended, and there is also one carry resulting from the previous one. Earlier what we have seen is for first output is S10, and here we see for S11, it is exactly same thing as that, and now we have added LSB as well as MSB. So at the next clock edge we are going to register the MSB to continue addition of MSB, so right, and this is at positive edge of the clock, and this is the clock 4, and here what we do is we also preserve the LSB which we have added earlier, and because finally we had to put them all together, MSB, LSB, and so that is the reason why we are preserving here. So all these are preserving the LSB, and this is preserving the MSB. Note that in the second stage we have only two outputs, and once again the last bit will be the carry, carry or the sign bit. So in the third stage addition, what we do is, this is the final output that we nomenclature as, and from second stage what we got was S10 and S11, and that was only LSB, and therefore we had to add the two LSBs of the second stage, and add LSB first. S20 LSB 7 is the carry here, this is the carry, and what we will do is with the arrival of the next clock, that is clock 5, register MSB to continue addition of MSB, and here what we do is just transfer it to another register, and note that only 5 is different from this. So that we just preserve all MSBs here, and for S0 as well as S11, and oh sorry, that is here. Addition of MSB, and preserve all MSB, and also the LSB sum here. So finally note that S20 is the output here. Here what we do is add third stage MSB result and concatenate with LSB result to get the final result. What we have done so far is we have added the LSB of the second stage as well as the MSB of the second stage along with the carry that resulted from the addition of LSB, and now we have total value available there, and in the form of two outputs, namely S10 as well as S20. This is the one, right. So this is LSB and MSB are here, and this is only I think this is only a carry here. So the final result is addition of two numbers that results from the output of the second stage, and that is basically S10 and S11, and we had to sign extend as we had done before, and that is what we had done here. The very same thing is extended here, and to that we have to add the MSB, because we have not done the addition asset, we have done addition only for LSB, and having done that one, that is from this one, and we have also to concatenate the LSB because we have added this in the previous stages, and that also we need to LSB will have to be concatenated. This is the flower brackets used for concatenation, and once again concatenation here, and just to separate out, I mean it is to sign extend here. So is the case with sign extension of this number. So the second stage MSB which are two in number, that is S10 and S11 are added here with sign extension, and to that we concatenate the LSB because we have added this earlier. So out comes the final sum here 14 through 0. This you can easily reason out. For example, here it is 7 bits here, and concatenation 8 bits here, and this also 8 bits here, and here it has 7 plus 1 8 bits here. So you are adding all this, this will be 8 bits, 8 plus 8 here, then plus 7 here. So totally 15 bits you will be getting, and this completes the design. We will go into the look into the test bench for adder subtractor design. As usual, we want to run at say 100 megahertz, so we define clock period by 2, and we need to have a back annotated file for adder, and we declare the test module, which is this, and we want to return only the final sum, and note that we had used only assign statement for the sum, and therefore it is not registered, and that is why it is in 5 clock cycles you could do, and if you want to register it you need one more clock cycle. Right now we do not want registration, and once again sum is declared, and all the inputs clock N0 through N7 are declared as register in the test bench, and then we invoke the actual design, which is added 12s, and instantiate here, and then list IOs. For example, clock and N through N7 are inputs, and final sum is the output. And then we start the real testing process by initializing with a begin and matching end, and in between at different points of time we will keep on changing the various inputs. For example, all the inputs are initialized to 0 here, and at 17 nanosecond, so let us say we apply a different number. In this case, all f means all ones. All ones means we have seen in 2's complement representation it is -1, and all of them we are going to add -1 here, we are going to add all zeros here, So, and after 20 nanosecond we are going to change again to a different value. Here it is 2047 or something, which we will have a look at the waveform, then we will be clear. And initially we have staggered a bit here 17 nanoseconds just to make sure that data is stable before the clock arrives. And every 20 nanosecond we are changing here. I am sorry, I mentioned as 100 megahertz, but it is actually 50 megahertz because the loaded value is only 10. So, that is only half the time period, therefore, it must be 20 nanosecond time period, and hence clock will have to be 50 megahertz. And we change another set of data to 800, then all ones. We will have a look back when we see the waveform, and once again different one, +1, -1, +1, -1. So, you can very easily compute the sum orally where possible. I have also jotted it down separately, so we can compare with that. And once again here we can see one number here and another number, and so is the case here with all 1010 pattern and 010 pattern here. And once again we, I think this is the final thing, once again we have all zeros here, and after giving some cushion we of 400 nanoseconds we stop, and this completes the test bench. And we have finally in the test bench toggling of the clock, and this is the statement which is responsible for making a free running clock using an always statement, and the module ends here. And before we go on to the simplify results, which is here, and we will first see the waveform. So, before zooming I will just explain. Earlier we had applied in the all zeros here, and sum must be naturally 0, and let us see where that sum happens here. So, that is not the one, this one. So, all of them are zeros here, and then all are I have just noted down, let me make sure that they are okay. So, 8 into 0 here, it should then 8 into -1, and 8 into 2047, and then minus 2048 we have once again 8 numbers here, and 8 into 1, and then 1 -1, 1 -1. So, this should give 0, that is I have noted down here as 4 into 1 -1 into 4, and then comes 4 into 2047, these are all plus values. Then we can say this minus is we can take it out, -4 into 2047. So, naturally this should give us 0 again, and so I have just noted down as 4 into 2047 minus 2047, and next value is minus 1366 plus 1365. The same thing happens in pairs here, and that is noted down as 4 into minus 1366 plus 1365, which gives a sum of -4, and finally we have all zeros here, that is 8 into 0. And so, I will zoom this here, and let us say we have already seen that there are 5 pipeline inside. So, naturally the result must manifest only after 5 clock cycles. Let us have a look whether it is so. The result starts here, you can see 0 here, this result. After zooming you will be seeing it clearly. Right now just be content with the waveform that you get here. So, 1 pulse here, 2, 3, 4, 5. So, after 5, after a further delay, almost some 5 nanosecond delay is here, and or more, and the result manifests here. This is because of back annotation. Actually, without back annotation you should have got right at this edge. Because of back annotation, gate delays will come into picture, and the result gets only after a delay, and clearly it is after the 5th clock pulse, and that is what we had designed for. We will zoom it here and see what the results are. So, these are all the 8 numbers what we have already seen, explained here everywhere, and the final line is the sum, and very first sum, this is 8 into 0 as I have mentioned here. So, 8 into 0 is 0, and that is what is here, and next one is 8 into minus 1, and answer must be minus 8. So that is also here, and because the cursor is there, it appears to be something else, it is actually minus 8. And next one is 8 into 2047, so it should yield 16377, and that is also correct here. And the next one is 8 into minus 2048, and the result must be minus 16384, and that is correct here. And we have one more waveform, and this also I will zoom here, which will continue from the previous one. So once again some more this the last data, all of them are zeros, and first one is the clock, and final sum is here, and we have already seen minus 1630 and 84, just overlapped so that you will have continuity in visualizing this. So next one is 8 into 1 as per my list, and it should give a sum of 8, that is what we have here. And next one is 4 into 1 minus 1 into 4, that must produce 0, that is also there. So and there is one more 0 here, let us find out whether it is so. Next value is 4 into 2047 minus 2047, and that naturally produces 0, that is what is here. And the next value is 4 into minus 1366 plus 1365, and this is 4 into minus 1, so that means minus 4, so that is what you have here. And finally 8 into 0, that must produce 0 result, that is what you have here. So this proves that the addition is working, and all of them are signed numbers, and we will have a look at the simplicity results for this. And so it works at a clock of 112 113 megahertz. This is simplified results, synthesis results, and we have mapped as usual on the standard device for the reasons we have mentioned earlier, and this is the design, and various internal primitives are all listed here, and finally a number of LUTs will also be listed here. It takes only 95, although it says 0%, it can't be really 0 there, it is a fraction less than 1%. So that is the simplified result, and here comes the Xilinx place and route results, and you have all the slices, flip-flops, LUTs listed here. And what is of interest is number of gates standardized to say 2 input NAND gates, and it comes to around 8,000 gates nearly for a single adder, which adds 8 numbers of 12-bit signed numbers. And now surprisingly Xilinx reports much higher frequency here, say 152 megahertz, that's, and also produces a dot bit output, bit stream output. And so next we will consider is in the arithmetic circuit we will consider multiplier design, and this is a new algorithm developed by the speaker, and for the sake of implementing on FPGA as well as ASIC, yielding as high a throughput as possible. And this is primarily because I was designing DCTQ and all the compression algorithms, and which demands a very high throughput, and we will have to process some very high resolution pictures colors such as 1024 by 768 resolution, and all this necessitated heavy pipelining, and also massively parallel circuits. And it may, mention may be made that FPGA ASICs are primarily massively parallel and highly pipelined, and these are all important characteristics of FPGA ASIC field when compared to the microprocessor and DSP processors, wherein you do not have this much massive parallelism or pipelining, heavy pipelining. And because of those two, that is parallelism and pipelining, and on the high end we get a very high throughput. And this particular multiplier is simply a signed multiplier for multiplying two numbers, say of this dimension, for example 11 bits. This is arising from DCTQ application point of view, and one number is here and another number is 8 bits 7 through 0, and we nomenclature it as multiply 11s into 8s here, and the final output naturally will be sum total of all the bits, that is 18 through 0, which is 19 bits. Here you have 18 here and 8, so I am sorry 11 here and 8, so 19 bits it should produce, and that is what it is. And before we go into the details of the algorithm, let me make a mention that this multiplication is done primarily as a magnitude, and therefore first what we will do is separate out the sign from the magnitude and process apply the algorithm only for the magnitude, and we can deal with this sign separately, and which turns out to be a simple exclusive OR gating. And finally, and before we consider the algorithm, let us take an example. We want to evaluate the product for two numbers, let us say 1023 and to minus 128. This happens to be the last possible value in each of these two numbers. This is corresponding to n1 and this is corresponding to n2, that is what it is here, and the algorithm works on magnitude primarily, and although sign is automatically incorporated, and internal evaluation are all in magnitude. And let us take this example. If you write this in binary fashion, you will see that all of them are 1 here, and 1 will be the MSB here being a negative number. If you evaluate this, you see that it is 128 here, 4 plus 3 7 bits here, the 8th bit is naturally is the weight for 128, and final result will be this in 2's complement fashion here, and this corresponds to minus 13 0 9 44, and as mentioned before, we will take only the sign of this numbers, and which is this here. This happens to be exactly the same, and for 128 minus and plus happens to be the same, and this being a positive number, and automatically the same number is put here for magnitude. So we can evaluate magnitude merely by taking 2's complement of any number. For example, if you want, you can take a 2's complement of this, and then out comes the magnitude of this number, and we can identify this number as a negative number by inspecting the MSB, which happens to be 1. And now how do we compute multiply in the usual way? We are going to go into the algorithm now. So when we take two numbers, we take the first bit and then multiply all this and then put here. So here it happens to be all zeros because we are going to multiply with 0 here, and out comes 0. So is the case for all other 0 bits, and every time we shift by 1. This is what you do while hand computing, and the final one is 1, therefore the same gets duplicated here, and with of course a 1 bit shift. And the usual fashion, what you do is just add here, and bit by bit you add along with the carry, and finally this will be the result as far as the magnitude is concerned. And let us nomenclature each of this partial product, which is the multiplication of n1 with single bit of n2. The LSB bit will be the first here, and all other bits will be in this fashion, and out comes this result, and this is in magnitude form, whereas what we have put here is it is in 2's complement, which signifies a negative number. This and the last number are equivalent actually, so we can find it out from this. Say for example, if you take 2's complement, as I mentioned, you will get the magnitude straight away. So we are not bothered about the negative number, because what we are interested is only evaluating the magnitude. So what we do is we apply the 2's complement. So we just start inspecting till you encounter 1 here. This is what is here. So retain all these numbers as it is, and then invert all the other bits. If you invert all the other bits, all this will become 1 here, and this will become 0. That means say 3, 4, then 7, 10 ones will be generated here, and apart from this 1, 3 plus 3, 7 zeros here, 1 7 zeros, right, 1 7 zeros here, and apart from that we have 3, 6, 9 bits here. So is it same? 3, 6, 9, why 1 is there? Maybe because of sign extension here, or is there a mistake there on the top one? You cross check this. right, even if there is 1 0 not there, the same result will be same anyway. So, I might have put by mistake one extra 0 there. So, this algorithm goes like this, it is pictorially depicted, and we have once again used bit partitioning as well as functionality partitioning, and here also it happens to be the functionality will be basically add or subtract, and this is once again in 3 stages as we have seen the adder before, and only extra thing that is coming here is we need to do left shifting either 1 bit or 2 bits or 4 bits. I will explain this is the typical case of this new algorithm, and now what we have seen in this previous example is P1 through P8 as being partial product. So, in the Verilog code that we are going to consider, we will see how P1 through P8 are arrived at. It is for the time being this is sufficient if you just add the P1 and P2 to start with, and when you do this one we have 4 such adders here which will add 2 numbers at one stroke. So, in concurrently you will have all the partial product results here, and that is what we said before, that FPGA or ASIC design is characterized by massively parallel circuits. That is what we have here, and when you see DCTQ you will be astounded by the parallelism that will be built in. And so also it is highly pipelined in sense that there are internally there are so many pipeline registers. For example, 2 registers are hidden inside, and that is the reason why clock has been input there, and so is the case here, 2 more here and again 2 more here, and in fact if you see the clock, we have the very first clock. In fact, the very first clock will register this P1 through P8, and then in fact N naught through N naught and N1 are the actual inputs that will be registered first and followed by this registry, and then only the with the next arrival of the next clock pulse only we reckon it as first clock in order to do the internal processing, and we need 1 through 8 clock pulses. They are all internally there are pipeline registers here, and there are basically 3 stages of addition, and also there is a shift here that is happening inside here. And in Verilog shifting is very easy, we have only to take the relevant bits, and therefore it is the whole multiplier is reduced to mere addition, nothing more, addition or primarily addition, because 2's complement even sign is taken care by mere addition, and so the algorithm turns out to be very straightforward and simple. And here what we do is we add, earlier we have seen the partial products are P1 through P8. What we do is we add these 2 and concurrently we add this 2, this 2, this 2 by the 4 adders of the first stage that we have seen. Out comes the result. Now while adding this one, note that we do not have to add this first bit, because you know that there is nothing, no matching number here, it is equivalent to having a 0 there. So when you add 0 and 0 you will get 0. In this example all happen to be 0, but do not jump to conclusion that all can be done in this fashion. It is applicable only for the first bit. There may be other numbers where they will all be non-zeros, including this, and even if it is a non-zero, that is 1, if you add 1 or 0 to 0 you will get the same number. Therefore we do not have to add this. What we have to do is rest of the number, what we will do is we will take the entire thing, bifurcate by 2 and call it LSB and MSB, and then add at every clock only LSB, and then the second clock, following clock we will add the MSB as we had done before in the adder case, and we will follow the very same pattern here, and at every stage it is going to be same. The subsequent addition will be there will be a result arising from this. That result will be added in the second stage, and naturally for 8 numbers you will have only 4 outputs, because there were only 4 adders, and those 4 outputs will be taken 2 at a time. Once again have second stage of addition and add 2 numbers at a time, and out comes one result, and there will be 2 such outputs, and those 2 we will add in the third stage and resulting in one final sum, and all this would be registered at different points of time. In total we have 8 clocks, and therefore 8 pipeline stages inside, and hence 8 pipeline registers as well, and that is what we have seen here, and let us say S11 through S14 are the intermediate results arising from the first stage of addition. So now what we had to do is we did not say what this LS1B is. So P1 P2 if you take in the example here, P1 P2 if you inspect these two terms partial products, so what we see is this P2 is staggered a bit, so it is as good as left shift by 1 bit here. So that is precisely what we are doing for P, not only for P2 but also for P4, then P6 as well as P8. So you will see left shift by 1 bit as far as the first stage of addition is concerned, you can see here. So P2 is left shifted by 1, then only added to P1, and here when this is clock 1, corresponding to this there will be internally a register, and that will register the sum of LSB alone. What we have seen is total number is bifurcated into two, say calling roughly half, one is we call it as LSB, the other half we call it as MSB. So we add only the LSB here, and carry will result, which will add with the MSB of these two, and at this second clock here, and then concatenate the two and to make one complete S11 sum there, and like this we will have 4 such results, and these two will add, and this time we had to, in the second stage of addition, what we had to do is we had to left shift by 2 bits. Why we will explain in a minute. So similarly S13 and S14 are added up, and once again this S14 is left shifted by 2 bits and then added up, and once again this LSB will be added first in clock 3, and in clock there is one extra clock because the bit precision has increased now in this internally, and it will be increasing progressively. So we want to give a little more cushion, and therefore we spend one more clock. You can experiment with this to see whether we can reduce the clock, and there may be some scope for you to reduce. Instead of 8 pipelines you may get even 6, and you can experiment with it, and in fact this is not really required, because what we are going to do is pipeline the whole not only the multiplier but also the entire process. Even a complicated algorithm can be pipelined totally, and all these pipeline delays will only be a one time affair. Therefore we not really bother about extra additional pipelines, and higher the pipeline that you do, and higher will be the throughput, that is speed of operation will be much higher. So that is a desirable thing, and of course you have to pay a price of additional this pipeline registers, and that will be only a marginal increase. So you are free to do as many pipelines as possible. So we will explain why these 2 bits here. What we are doing is we are taking the sum of the first stage here. If you look at this example once again, what we are doing is we are adding this, and out comes the result here, and we are adding this, and there will be a result here. Those 2 results we are trying to add. So naturally the first result is taken as such, and whereas the second result is shifted by 2 bits, because if you see the second group, it is shifted by 2 bits from the first group. This is the first one, and corresponding first partial product is this one. Therefore there is a 1 then 2 shifts here. Therefore the second stage of addition will have 2 shifts. Likewise if you those 2 will produce, when added in the second stage, one more output, and similarly from this you will get one more output here. So notice that this the last stage there will be 2 inputs, and those 2 inputs are staggered by 4 bits, because it is the result of these 4 first here and this 4 here. So when compared to the first one and this second group, you have 4 bits, 1, 2, 3, then 4. So the third stage will be 4 bit shifted, and that is how it is. So this is the specialty of this novel algorithm for the multiplier, and there are scores of other algorithms. You are free to look into those, and you can make a comparison, and in fact all algorithms are good enough, and you are free to use any of that. Once you use the pipelining approach, it does not really matter which particular algorithm you use. What is important is how efficiently we do, and and you can see here 2 bits shifted the partial product the first stage, and final stage when you add the 2 numbers, once again there is a left shift of 2 bits here for the second number. So is the case here, when we add these 2 numbers, the second is shifted by 2 bits, this is the second stage input, and for final stage we see that it is shifted by 4 bits for the reason we have explained all. And finally the result is in 19 bit as we have seen before, and so this explains the algorithm, and we will look into the Verilog code for this algorithm. So we have 2 numbers n1 and n2, and n1 is 11 bit and n2 is 8 bit here, and both of them are signed numbers, and internally we are going to remove the sign for the temporarily, and then apply the algorithm in, only on the magnitudes, and having got the final result we will sandwich the sign bit and later on at the fag end. So now here we have n1 and n2 which is 11 bit and 8 bits, and 11th and 8 bit will be the sign bit, and so this particular thing as I mentioned before is for DCTQ application, and in that DCTQ application we need to evaluate matrix 8 by 8 matrices. For example, Cx is a matrix we will have to evaluate, and it will create some partial product, and that is what is being used here as n1, and this is the multiplicand and is signed, and in this case second number this is a cost term. So in DCTQ it is a basically cosine transform that we are going to evaluate, and for that we need some cost terms, and these are all stored in ROM table, the design of which we have already seen before in the ROM design, and we also mentioned that it was with the end goal in mind that we had taken all these examples such as ROM, RAM, dual RAM, and so also the adder what we have seen here, and as well as the multiplier that we are trying to look into, and all these applications are with the end view of using in DCTQ application, which is for video compression used for JPEG and MPEG, and this is the signed multiplier, and we have a multiplicand and a multiplier, and the final result which is sum of it is basically an evaluation of 3 matrices Cx and Ct, and we had assumed Cx is already available, and Cx can also be evaluated by using a similar multiplier, and which we will consider later on, and this result is in 2's complement. So now we will see the actual design. This module has 8 pipeline stages to increase the speed, and we should make a mention that input is not registered here. Straight away it may be registered elsewhere. For example, it is coming, these are all the inputs supplied from the ROM table or from the dual RAM table which we have already seen, and you notice that if you remember correctly, you would see that there there are registers at the output for both dual RAM as well as ROM, which we had seen in the design before, and because the those are already there, the registers are already there, we do not have to register the inputs. So we can straight away take, and this is the module name that we declare here. So module multiplier 11 into 8, and S stands for signed. So this is the module design name we have given, implying that it is a signed 11 bit, and we have clock as input, then 2 numbers must be there as inputs n1 and n2, and final result is also listed here. So all the IOs are listed here, and the bits are also mentioned here. So for example, input here, then n1 and n2 are inputs 11 bits, and then 8 bits here, final result is 19 bits, and here what we are doing is, so we are whether it is whether there are 2 numbers n1 and n2, whether it is a 0 or not, we have a separate flag for that. That is what is declared here, and there are so many we have seen that partial products here earlier, and that is of 11 bit, and we need to declare them as wire, since they are all basically evaluated as a assign statement. So is the case at first stage addition we have seen S11 through S14, that is what is here, and there also combination to start with, especially the LSB portion, and even MSB portion it will be primarily an assign statement, and later on we will be registering in the succeeding clocks, and you can see like this so many signals are used here, that is for the first stage, and this is for the second stage here, and this is for the third stage. You have then final result, the sign also is required, we have to keep track of it, because we are evaluating the magnitude using the algorithm, the magnitude for the two numbers n1 and n2 are declared as register, which we will be evaluating, and that is what is here, and we also declare other registers which happen to be in always block, and they are all at different clocks. For example, clock 1, any registering you do for partial product, that we give another extra reg 1, that is the nomenclature adopted by us here, and similarly there are other for other pipeline stages, for when clock 2 strikes we will have intermediate results in reg 2 and so on, and we also need to propagate the number sometimes, so that is what we do here. And for n1 as well as n2 here, and what there we will see when we start analyzing the code. We will continue with this in our next class. Thank you.